A series in numerical methods in civil engineering, we are going to talk about error bounds for linear systems. However, before doing so, we want to talk about one other method for solving linear systems in a cheap and efficient manner, a method which is particularly suited for positive definite matrices. And as we know, in civil engineering applications, we encounter a wide number of positive definite symmetric matrices in numerous applications. Particularly useful compact form for positive definite matrices is given by Choleski decomposition. It is based on the following theorem, which says that for a symmetric positive definite matrix, there is a unique upper triangular matrix with positive diagonal elements such that A is equal to R transpose R. Let us recall our LU decomposition, where we said that A can be written as the product of a lower triangular matrix and an upper triangular matrix. This is much more narrower than this. This criteria is much more narrower than this. It says that A is equal to R transpose R. So basically what we are saying that A can be written in terms of an upper triangular matrix, and the lower triangular matrix is just the transpose of the upper triangular matrix. Recall from the LU theorem, we have A is equal to LU, where U11 is equal to A11, which is positive, U22 is equal to A222, and using the transformation rule for LU decomposition, or for Gauss elimination for that matter, U22 is basically A22 minus A12 by A11 by A21, which can be written as determinant of A2 by determinant of A1, where we recall determinant of AK with k can vary from 1 to n. AK is the submatrix formed by the intersection of the first k rows and the first k columns of A. So A2 is the submatrix of A, which is formed by the intersection of the first 2 rows and the first 2 columns of A. So U22, the second element in the second diagonal element, is nothing but determinant of A2 divided by determinant of A1. And for positive definite matrices, we recall that all these submatrices for k equal to 1 to n, that is all these submatrices A1, A2, A3 up to An, they must all have positive determinants, right. So what does this mean? So it means that U22 must always also be positive, since determinant of A2 will always be greater than 0 and determinant of A1 will always be greater than 0. Similarly, we can show that for any k, UKK, the kth element on the diagonal of the upper triangular matrix can be written as determinant of AK divided by determinant of the submatrix of one order less than AK, that is AK minus 1. And since this is a positive definite matrix, both determinant of A and determinant of AK minus 1 are positive. So that guarantees that UKK will always be positive. So next, let us introduce the diagonal matrix D, whose diagonal elements comprise the elements which we just computed, U11, U22 through UNN, which we just defined, which we just showed how to compute just before this. In that case, the decomposition, the LU decomposition, can be written as A is equal to LU. We can write it as L D inverse U, which is identical to LU, and then write L equal to L D U prime, where we define an intermediate matrix U prime is equal to D inverse U. It is clear that both L and U prime are unit triangular. L by definition has got 1 on its diagonal. So L by definition is unit triangular, and now when we have defined U prime is equal to D inverse U, U prime is also going to have unit values on its diagonal, because D inverse contains the inverse of the diagonal elements. So D of U, so D inverse U will always going to have 1 on its diagonal. So, U prime is going to be an upper triangular matrix, only difference with U is that it has got 1 on its diagonals. So, now we can write A is equal to L d U prime, where both L and U prime are unit triangular, and also they are uniquely determined by the LU decomposition according to our theorem earlier which we encountered, which says that the LU decomposition, when it exists, it has to be unique. Since A is symmetric, we can write A is equal to A transpose, which means from this expression on the right, from the last equation, which means that A transpose is equal to U prime transpose DL transpose. So, comparing this equation with the equation A equal to L d U prime, you can just by comparing terms, we can show that L transpose is equal to U prime, which is equal to D inverse of U. Next, we denote R, another matrix, with as D minus half U, where D minus half has positive diagonal elements U, K, K minus half. So, R is nothing, R is D minus half U. D minus half, how do we form D minus half? D minus half is D, we already know how to form D. We have formed D by just taking the diagonal elements of U, and D minus half, we just take the square root of the diagonal elements. It is just the square root of the diagonal elements, of course 1 by the square root of the diagonal elements. And if we define R is equal to D minus half U, then we can write R transpose R is equal to U transpose D minus half transpose, which is identical to D minus half, since D minus half is a diagonal matrix, D minus half U, which is equal to U transpose D inverse U. But let us recall L transpose is equal to D inverse U, which we obtained earlier. Therefore, D inverse U is equal to L transpose. Therefore, R transpose R is nothing but U transpose L transpose, and taking the transpose of both sides, we get R transpose R is equal to LU, which is equal to A. Thus, this shows that it is possible to write A as the product of a matrix R, its trans and its transpose. And this also shows that it is always possible to write U is equal to L transpose for positive definite symmetric matrices. Let us go back to the LU decomposition and recall that for the kth step of the LU decomposition, we use the following equation. AKJ is equal to sum over P equal to 1 to K MKP UPJ, where J is greater than or equal to K. That is, we are constructing the part which is above the principal diagonal, or at or above the principal diagonal, and AIK is equal to sigma P equal to 1 to K MIP UPK I greater than K, which is the part which is below the principal diagonal. We can write this as AKJ is equal to MKK UKJ plus sigma P equal to 1 to K minus 1 MKP UPJ. Basically, we are combining both these equations and writing it like that, where we have taken out the term, the kth term, and we have kept the rest of the terms within the sum. So, we can combine both the equations and write it like that. So, we can write in that case MKK UKJ, just by moving the terms to the left hand side, MKK UKJ to the left hand side, MKK UKJ is equal to AKJ minus sigma P equal to 1 to K minus 1 MKP UPJ. Also, so actually let me go back a little bit and maybe I should clarify this equation is nothing but this equation, and this equation we are going to handle in the next slide. So it's not that it is combined, I am sorry I misspoke, but AKJ is just this equation where I have taken out the term kth term outside the summation sign. In the next slide we have the second equation, which is AIK is equal to MIK UKK plus sigma p equal to 1 to k minus 1 MIP QPK, which is basically this equation, this equation after I have taken out the kth term outside the summation sign, and we get that. So again, rearranging terms, we can write MIK is equal to AIK minus sigma p equal to 1 to k minus 1 MIP UPK divided by UKK, where now I is equal to k plus 1 k plus 2 through n. If U is equal to L transpose, then UKK is equal to MKK, right. So M are the diagonal elements have to be the same, while the off diagonal elements are just the transpose of each other. So UPK is equal to MKP, since U is equal to L transpose. Recall the elements of L are M comprise the elements of L, U comprises the elements of U. So since U is equal to L transpose, that means the diagonal elements have to be equal, UKK must be equal to MKK, and UPK is equal to MKP. From the previous equation, from star, for j is equal to k, we can write it as MKK UKK, which is, and we know UKK is equal to MKK. So the left hand side becomes MKK square, and the right hand side becomes AKK minus sigma p is equal to 1 to k minus 1 MKP UPK. Let us go back and see what it looked like. It looked like MKP UPJ, sorry, it looked like MKP UPJ, and we have replaced that and said MKP UPK, and that is equal to AKK minus sigma p equal to 1 to k minus 1 MKP square, because UPK is equal to MKP from the symmetry from U is equal to L transpose. So we can write MKK is equal to AKK minus sigma p equal to 1 to k minus 1 MKP square to the power half. What does this tell us? This basically tells us how we can go about our algorithm. So what this tells us is becomes clear if we look at the next slide. So this is our Choleski decomposition graph, and so this is a particular stage in our Choleski decomposition. Suppose at the kth step, right, at the kth step of the Choleski decomposition, where the red part is already known, that is the upper triangular part which has already been formed. The blue part consists of the multipliers which have already been formed, and the gray part is not known. Not known means it is still got to be modified, right. It is already, the original matrix is known, but it has not yet reached its final form after Choleski decomposition. So what this says is that at the kth step, what we are going to do is we are going to change this yellow part, this yellow strip, the yellow strip corresponding to this column and the yellow strip which corresponds to part of this row, this is going to be changed. So at the end of this step, this gray region will become smaller, it will become like this, and this part is going to, we are going to find the new values of this part. So how do we go about doing this? Well, the previous equation, this equation tells us how we are going to change the diagonal element. This tells us how we are going to change MKK, this term, which is basically the diagonal element here, and it says that how are you going to form the diagonal element? Well, the diagonal element is going to be formed by AKK, which is the existing value here, minus mkp square, where p is equal to 1 to k minus 1. So, this mkp square terms are the terms here, the terms on this row up to k minus 1. So, up to the diagonal term. So, as you can see, the information that it needs for updating this element is already known, because this has all this we already know the final form of this, and this is just the diagonal, the current value of the diagonal. So, it uses these two values, this minus this square to form the diagonal element. So, next let us look at how it updates the off diagonal elements. So, we know how it forms this element, we know how it forms the diagonal element. So, if we can next find out how we can update this column, we are all set, because since this is symmetric matrix, if we have updated the column, we have also updated the row. So, we only need to find out how to update this part of this column, and that is given by the second equation. The second equation, which is double star mik, this equation tells me how to update that column, and let us see how we do that. This equation can be rearranged as mik. Basically, I am rewriting this equation. Mik is equal to aik minus sigma p equal to 1 to k minus 1 mip mkp divided by mkk, I equal to k plus 1 through n. And you can see from our previous picture, so for instance, if we want to update this element on the column, we just need to take the product of this vector with that vector, right. So, this times that, I mean as a column vector, right. This is a row times that becomes a column vector, row times this column gives me this updated value. So, again, to compute the updated value, we only need terms in the blue or red regions of the matrix, that is, we only deal with terms which are already known, which is a significant advantage of this method. The right hand side of these expressions contain known quantities from the previous k minus 1 steps, right. So, this minimizes storage, this is more compact, and this method is known as Choleski's method or the square root method. Why is it called the square root? Because to compute the diagonal terms, we have to take the square root of this expression. But it is well known, I mean it is that computing square roots is expensive. The square root computation in any numerical, any computer, the square root is the most expensive, probably one of the most expensive numerical operations that you can perform, other than for instance taking trigonometric functions such as sine, cosine and so on and so forth. So, we would like to avoid taking square roots if possible in order to increase the efficiency of our computer program. So, what is normally done is that people decide to, instead of going through this process, instead of doing Choleski decomposition exactly as I discussed earlier, what they do is to go ahead with Gaussian elimination and then obtain the triangular matrix U and then compute the R matrix. So, we use this relation A is equal to R transpose R is equal to U transpose D minus half D minus half U. So, compute R in terms of D and U, and this allows us to write the decomposition of the system. It allows the decomposition of the system as A is equal to U transpose D minus 1 U. So, A is equal to U transpose AX is equal to U transpose D minus 1 UX, right, and then we write D minus 1 UX as Y. So, we write this system becomes U transpose Y is equal to B, and then after we have solved for Y, we solved for X by solving this system UX equal to dy. So, we solve two triangular systems, U transpose Y equal to B and UX equal to dy. That again it is noticeable here that L is nowhere formed. So, we are taking advantage of the fact that for a symmetric matrix, symmetric positive definite matrix, you can write, instead of A is equal to LU, you can write A is equal to R transpose R. So, we are taking advantage of the fact without having to compute the square root, which makes the Choleski decomposition expensive. Why don't we have to compute the square root? Because we are never explicitly computing d minus half, we are always computing d only in this way. So, this takes advantage of the fact that for a symmetric positive definite matrix you can write A as R transpose R, but it does not require taking the square root. And let us recall that but the prerequisite for this is to perform the Gaussian elimination, because we have to calculate U. But recall that for Gaussian elimination for positive symmetric definite matrices, we do not require any pivoting at all. So, Gaussian elimination for positive symmetric definite matrices is relatively cheap. Next, let us switch to a slightly different topic, which is related, but which is of very great importance, and when you are trying to solve practical problems which have got very large coefficient matrices. For instance, we often encounter symmetric positive definite matrices, for instance in finite elements, where the location of the non-zero elements differ greatly from row to row. For instance, in one row there might be if the row is n, the size of the row is n, you might have, it might be very fully populated, or it might be almost fully populated, while in another row or column it might have just a few non-zero elements which are probably localized near the diagonal. So, for these matrices we want to take advantage of certain special storage schemes, because we want, if there are a lot of zeros in a matrix, we do not want to store those zeros because they occupy memory, they increase the size of the matrix. So, if we can figure out a clever way of reducing the storage, we have, and the efficiency of our algorithm increases significantly. So, special storage schemes have been devised for such matrices. For example, various profile storage schemes, which have two goals. First of all, the reduce storage, they reduce the requirement to store all the zero elements, so they reduce the storage, and number two, they allow fast access to the elements of the matrix during the computations. When we are processing a matrix, then we want to access the elements of the matrix, we want to able to do it as fast as possible in order to reduce the computational cost. So, these special storage schemes have these two goals, so reducing storage and allowing fast access. One of the most well-known storage schemes is known as the Skyline solver, and in the Skyline solver, the upper triangle of each symmetric matrix is stored column by column, but not the entire column is not stored. In each column, only the elements from the first non-zero entry to the diagonal are stored. So, all zero entries for each column, all zero entries from the first entry up to the non-zero entry, they are not stored. So, only the diagonal and the first non-zero entries in that column are stored. The zeros contained between the first non-zero entry and the diagonal are of course stored, but any zeros above the first non-zero entry are not stored. So, matrix is thus represented by a vector S is equal to S1, S2 through S mu n, and in addition we need a pointer vector which contains the location of the diagonal elements. This pointer vector is mu, which has got n entries, with mu1 representing the location in S where the first diagonal element resides. So, for S, mu1 has always got to be 1, right, because for the first column the diagonal element is the first entry. So, mu1 is equal to 1, but mu2 gives me the location in that row vector S where the second diagonal element resides. Similarly, mu3 gives the location in that vector S where the third diagonal element resides, and mu n gives the location in S where the nth diagonal element resides, which always has to be the last entry in the S vector. So, if we want to extract element aij of the matrix where j is greater than I, then we can use this following rule, and which says that if j minus 1 is less than mu j minus mu I, which means that the element aij lies within the skyline, then aij is equal to sp, where p is equal to mu I plus j minus 1. So, this will become clear from an example which we are going to look at earlier. If on the other hand, if j minus 1 is greater than mu j minus mu I, that is the element aij lies outside the skyline, then we do not need to, we have not stored it in S, since it lies outside the skyline, we can by definition that aij is equal to 0. For instance, let us look at this matrix A equal to this, and you can see that in this matrix we are going to store only the elements in the upper, this is a symmetric matrix of course, and we are only going to store the elements in the upper triangular matrix which are below the first at or below the first non-zero term in a column. So, in the first column we are going to store 25 3, in the second column in the first column we are only going to store 25, which is the diagonal element, because we are storing only the elements at or above the principal diagonal. So, in the first column we are going to store 25, in the second column we are going to store 3 as well as 21, since 3 is non-zero, but in the third column we are not going to store this leading 0, we are only going to store 2 and 23, we are only going to store all the elements at or below the first non-zero entry in the upper triangular part of the matrix in this column. So, we are going to store 2 and 23. In the fourth column again we are not going to store this 0, we are going to store 4, but we have also got to store 0, because 0 is occurring after the first non-zero entry in the column. So, we are going to store 4, 0 and 22, but in the fifth column we are not going to store all these zeros. So, we are going to save a lot of storage, and then we are just going to store the diagonal element which is 20. Same thing for the last column, which is the sixth column, we are not going to store all these leading zeros, and we are just going to store 35. So, my S vector will be this. So, we have reduced the storage significantly. However, we also need to store this mu vector. This mu vector tells me which is the position in this column which has the first diagonal matrix. So, the first diagonal element is at the first entry in this column, so it stores 1. The second diagonal element, which is 21 is at the third location in this column, so it stores 3. The third diagonal element 23 is at the 1, 2, 3, 4, 5 fifth location in that column, so it stores 5. So, it stores the diagonal pointers, and it stores this skyline like this. So, the total storage of course is given by the length of this S vector and the length of the mu vector, and in this case we can see this length of the S vector is probably 10 and the length of the mu vector is 6. So, the total length of the storage is 16. However, how much have we saved storage by? If we actually stored the full upper triangular matrix, we would have to store n square by 2 terms. So, we have saved the storage by n square by 2 minus 16, which in this case is 36 by 2, that is 18 minus 16 is equal to 2, which the saving is comparatively less for this small matrix, but for real problems, real world problems where you can have 1000 by 1000 or maybe 100,000 by 100,000 matrices, you save a lot of storage by this profile, by using the Skyline solver. However, even if a compact storage scheme is adopted, it is of limited usefulness if successive stages of a numerical algorithm introduces a large number of non-zero elements. The efficiency of this scheme is because there are a lot of zero elements, that is why we can save storage. But suppose we start with an initial matrix which has got a lot of zero elements, but then during our Gaussian elimination a lot of those non-zero, because of pivoting, a lot of those non-zero elements become, a lot of those zero elements become non-zero. In that case again our storage is going to increase. So it is advisable to try a pivoting scheme which does not increase the number of non-zero elements. Hence it is desirable to use an algorithm which is both numerically stable and sparseness preserving. Why? Because numerically stable, because we know that unless we do pivoting for non-positive definite matrices we can encounter numerical instability. So some amount of pivoting is absolutely essential, but we want to also achieve the competing goal, which is that we want to preserve sparseness. Not only we want to ensure numerical stability, but we also want to preserve sparseness. Partial pivoting for Gaussian elimination is not normally advantageous from the sparseness preservation point of view. An alternative pivoting scheme known as threshold pivoting scheme can be adopted. In this pivoting scheme the pivot element is chosen to be a k. At the kth step the pivoting element is chosen to be a k prime k if a k prime k is greater than tau times maximum of mod of a I k, I is greater than k, and tau is a preset threshold value lying between 0 and 1. So for partial pivoting, for full partial pivoting, we look at the we choose as the pivot the element on the column in the kth column which has the largest absolute value, right. For partial pivoting we choose as the pivot the element on the kth column which has the largest absolute value. So basically for partial pivoting we would choose maximum of a I k I greater than k. That is what we would choose for full partial pivoting. But for threshold pivoting we are saying that we do not have to choose this maximum value, we can choose a value which is maybe if tau is equal to half, which is half this maximum value. If my pivot if at k prime which is of course less than I, the assumption is k prime is less than I. So I am going down from the kth row, I am moving downwards and I am moving downwards, and I am going to choose if I am going to do full partial pivoting, I will move downwards throughout the entire column and choose the element in that column which has the maximum positive value as the pivot. But now if I am not doing full partial pivoting, I do not have to choose the absolute maximum value. I can choose as pivot an element which is maybe half the maximum value, and if my largest maximum value is at a distance of 5 from k, and if my half the maximum value is at a distance of 3 from k, then if I choose 3 as the pivot rather than, if I choose a 3k as the pivot rather than a 5k, the possibility of my increasing the reducing the sparseness becomes less, because I am going to do less switching. Normally in partial pivoting the largest element of the column is chosen as the pivot. However, the row interchange following the selection of the pivot may adversely affect the sparseness of the matrix. Hence, instead of choosing the absolute maximum entry in the column as the pivot, we choose the first element of the column which is a certain fraction of the value of the absolute maximum entry, which it is seen this algorithm helps in preserving the sparseness. It is better at preserving sparseness than doing full partial pivoting. This helps achieves the twin goals of numerical stability of the computations, because we are doing some pivoting at least, as well as preserving the sparseness as far as possible. If tau is equal to 1, then of course the usual partial pivoting is obtained. During elimination, some of the zeros of A which are contained between the first non-zero element in a column and the diagonal will be replaced by non-zero elements. This is not a problem, because our profile storage scheme accounts for that, because we store all the elements which are below, at or below the first non-zero element in a column. So, if there are zeros below the first non-zero element, we automatically store it. So, that is not a problem. Next, so with all that discussion, next we move on to our main focus in this lecture, which is error analysis of linear systems. In practical solutions of linear systems, Ax is equal to b, elements in both the coefficient and the right hand side b are approximate, particularly when A and B represent certain physical quantities. There is always going to be, maybe A and B have been obtained from experimental data, so they will always be approximate. Recall from earlier, bounds on the error in the results of simple arithmetic operations such as addition, multiplication, etc. depend on the errors in the operands. For instance, we found bounds on the errors in addition, and we said that bound on the error in addition is bounded by the sum of the error in the operands, right. Similarly, we found errors in the bounds on the errors in multiplication and division. Also, we looked at bounds on the error of a function due to errors in the independent variables. So, if y is equal to function of x1, x2, x3 to xn, then we found a bound on the error in y if we know the errors in the independent variables x1 through xn. So, we derived that relationship. These results can be used to bound the uncertainty in the solution x due to discrepancies in A and B. So, due to discrepancies in A and B because of errors, we want to find out what will be the maximum possible error in x. So, suppose we know the error in A, suppose we know the error in B, we want to find out what will be the maximum possible error in my solution x. In addition to the errors in A due to discrepancies in A and B, additional round-off errors accrue during numerical solution of x is equal to A inverse B. Bounds on these errors too are desirable. So, there are two sorts of errors in linear systems. The first sort of error is due to discrepancies in the values of A and B, when there is some error in A and B are not known exactly, because maybe they are coming from experimental data. So, there are errors in the elements of A and the elements of B. But then there are additional errors which accrue during the Gaussian elimination, or whichever solution procedure we adopt to solve x is equal to A inverse B. Additional errors will accrue during the solution. So, we want to know bounds on those errors too. One simple way to get an estimate of the error during the numerical solution of Ax is equal to b is to compute the residual vector. That is, after we solve for x, we compare r is equal to x minus ab. Actually, this should be A inverse b, x minus A inverse b, because we have solved for x by taking A inverse b. So, we compare that x is equal to A inverse b, and we get our residual. If the solution is exact, the residual is exact, r is equal to 0, and one may assume that the smaller the value of r, the more accurate the solution, right. So, the residual is 0. So, then we can say that my solution is more correct. However, this is not always true for ill-conditioned systems. Let us consider the system A with a coefficient matrix A given by the matrix in square brackets there, and B by the column vector given there. So, suppose we get the solution of this system as x is equal to 0.9911 and minus 0.4870. In this case, r is equal to ax minus b is given by minus 1 into e to the power minus 8 and 1 e to the power minus 8. So, the residual is very small. However, the exact solution for this problem is x is equal to 2 minus 2. So, even though the residual is small, ax, where x has been computed by solving that linear system, ax is differing from b by a very small magnitude, by minus of magnitude by a column vector whose largest value is largest entry is 1 into 10 to the power minus 8. However, even though the residual is small, the exact solution is way off. Thus, in this case, although the norm of the residual vector is extremely small, the error is large. Why is this so? This is so because my matrix A is extremely ill conditioned. It is extremely ill conditioned. So, this will become evident if we look at the Gaussian elimination of this system, where at the second, after eliminating x1 at the second step, we get a22 x2 is equal to b2, and if we calculate a22, it becomes 10 to the power minus 8. So, this system by definition has got very poor numerical stability. Since the pivot is extremely small, very small changes in a22 will lead to large changes in x2. So, basically my solution for this system by Gaussian elimination is going to be arbitrary. Minor changes, minor perturbation will give very large differences in the solution. So, for ill conditioned systems, the size of the residual is not indicative of the error at all. So, that's for ill conditioned systems. Therefore, we have to figure out some better way to decide how to figure out the norm of the error and then to bound the error, to decide what are the possible bounds on those errors. To quantitatively discuss errors in the solution of linear systems, we have to decide on measures of magnitude of error. Recall the L2 norm of a vector and a matrix, which we discussed earlier, is given by norm of a vector x is given by root of x dotted with x, and the norm of a matrix, L2 norm of a matrix, is given by the square root of the inner product of A with itself, that is Aij. The infinite norm is given by, for a vector, x infinity is equal to maximum of xi, maximum of the absolute value of xi for I is equal to 1 through n. And the infinite norm of A is given by maximum of I lesser than or equal to I greater than or equal to 1 lesser than or equal to n, sigma I equal to 1 to n mod of Aij. So, basically we are summing the absolute values of all the entries in a row, and then we are taking the maximum over the column, maximum over each column. So, for basically what we are doing is that we are looking at it row by row, and we are summing the absolute values of the entries of all the elements in that row, right, and then we are taking the maximum of those values over all the rows. So, that gives me my infinite norm of a matrix. In general, if a matrix and a vector norm satisfies this relation, which is norm of Ax is lesser than or equal to norm of A times norm of x for any A and x, then the norm is said to be consistent. So, both my L2 norm and my infinite norm are consistent norms because they satisfy this relation. Norm of Ax means the norm of the vector which is given by Ax is lesser than or equal to the norm of A, which is a matrix norm, times the norm of x, which is a vector norm. So, if any norm satisfy this relationship, then for any matrix and any vector A and x, then the norms are said to be consistent norms. So, we will use these norms to develop error bounds for the linear system, assuming A and B are known, and then try to estimate the effect of perturbations in A and B. First, let us assume that we have perturbations in B only. So, we do not know exactly what B is, we know B plus delta B, where delta B is the perturbation in B. Because there is a perturbation in B, the solution to my linear system is no longer going to be x, it is going to be x plus delta x. So, Ax, I am going to solve the system Ax plus delta x is equal to B plus delta B. So, this gives me Ax is, since Ax is equal to B, this gives me delta x is equal to A inverse of delta B. And if for any consistent norm, recall how we have defined consistent norm here. So, for a consistent norm, this has to be true. So, delta norm of delta x must be lesser than or equal to norm of A inverse delta B, and this norm of delta x must be equal to norm of A inverse delta B, and norm of A inverse delta B must be lesser than or equal to norm of A inverse times norm of delta B, since my norms are consistent norms. Next, let us consider the effect of perturbations in A, that is delta A. So, A is not known correctly, so suppose we just know A plus delta A. Again, the solution is going to change, the solution is no longer going to be x, it is going to be x plus delta x. So, now we have the equation A plus delta A, x plus delta x equal to B. So, we have A delta x plus delta A, x plus delta x is equal to 0, because again Ax is equal to B. So, Ax and B cancels out from both sides. This gives me delta x is equal to minus A inverse delta A x plus delta x. Again, for any consistent norm, delta x is equal to norm of A inverse delta A x plus delta x, but norm of A inverse delta A x plus delta x must be lesser than norm of A inverse times norm of delta A x plus delta x, which must again be less than norm of A inverse times norm of delta A times norm of x plus delta x. So, we get this expression, and dividing both sides by norm of x plus delta x, we have this expression norm of A inverse norm of delta A by norm A. Norm of A, of course this is cancelling out, norm of A inverse norm of delta A, and this quantity is what is known as the condition number of a matrix, which is basically, this quantity is known as the condition number of the matrix, norm of A times norm of A inverse. And actually there is a printing error here. So, this is actually norm of A times norm of A inverse. The inverse should be inside the norm. So, norm of A times norm of A inverse times norm of delta A by norm of A. So, this is the condition number times norm of delta A by norm of A. Ka is the condition number of the matrix A with respect to the current norm. If the condition number is large, then from star small relative perturbations in A will produce large changes in x. Let us look at this expression again. So, if my condition number is large, small relative perturbations in A, that is small values of, if norm of delta A by norm of A is small, but my condition number is large, then my solution, the change in the solution will also be large. So, this is very important, the condition number is the crucial factor. So, even for small changes in A, when norm of delta A is small, I am going to get a large change, my error is going to be large if for a large condition number. So, again let us recall norm of delta x is lesser than or equal to A inverse norm of delta B, which we obtained earlier. which we obtained earlier. Norm of delta x is lesser than or equal to norm of A inverse norm of delta B. So again, dividing both sides by norm of x, norm of delta x by norm of x is lesser than or equal to norm of A inverse norm of delta B by norm of delta x. Since Ax is equal to B, we can write norm of B is equal to norm of x, and again because the norms are consistent, we can write this is less than or equal to norm of A times norm of x. So 1 by norm of x, from this expression 1 by norm of x is lesser than or equal to norm of A by norm of B. Then because of this, norm of delta x by norm of x is lesser than or equal to norm of A inverse norm of delta B norm of A by norm of B. How do we get this? Well, we use the previous relation which we got here, which says that delta x by norm of x is lesser than or equal to norm of A inverse norm of delta B by norm of x. So we use that relation here to get this expression, and again we identify norm of A inverse times norm of A. So here it is right? So it's norm of A inverse, not A norm of A inverse. So norm of A inverse times norm of A, that is the condition number of A. This is equal to norm of delta B by norm of B. So again, this again shows that if the condition number of K is large, then small perturbations in B is going to give me large relative changes in x. So in both cases the condition number is crucial. So in the previous case also we saw that if the condition number is large, then small changes in the coefficient matrix are going to produce large changes in the solution. Similarly, here we show that if the condition number is large, small changes in the right hand side is also going to lead to large relative errors in the solution. So the condition number of a matrix is a very crucial quantity in determining how much is the error going to be if either my coefficient matrix or my right hand side is slightly off, has got errors. Thus, in general, for ill-conditioned systems, minor changes in the input data, that is the values of A and B, will produce large changes in the solution X. However, it is not straightforward to calculate the condition number. Why? Because if you have to compute the condition number as the norm of A inverse times norm of A, we have to first invert A, and the inversion of A is a highly expensive operation. So it is not always useful, or it's not always practicable to compute the condition number. So we have to come up with certain other ways of computing the bounds on the error in a linear system, but a condition number, if known, that gives me very detailed information about the error bound if there is an error in the coefficient matrix or in the right hand side. So in the next part of this lecture we are planning to talk about errors due to round off. So up till now we have talked on errors due to imperfect knowledge of the coefficient matrix and the right hand side. However, Gaussian elimination, so if suppose we know our coefficient matrix and our right hand side, and then we do the Gaussian elimination, but Gaussian elimination involves a large number of floating point operations. The accumulation of round off from these individual floating point operation is also going to lead to more errors. It's going to accumulate, the errors are going to accumulate. Therefore, it is necessary to obtain a bound on the overall round off error due to Gaussian elimination, but in order to do that we have to bound the errors due to the individual floating point operations, and we are going to talk about this in the next lecture in this series. Thank you very much.